एक गुने आ जाएगा। एक भी नहीं बनाना, दूसरा आ जाएगा। ठीक है। Okay, let's see. Okay, so let's continue with the uh, kinetic theory of the gases. So in the last class, we had also seen the assumptions that are made for the kinetic theory of the gases. Okay, so what all assumptions they are made? That we had discussed here, the assumptions that were made. Finally, we discussed the three gas laws and we arrived at the ideal gas equation. So this equation we call as the ideal gas equation. We have the ideal gas equation given by PV is equal to nRT. PV equals to nRT, where P represents pressure, P represents pressure, N represents number of moles, N is the number of mole, and R represents universal gas constant. This is universal gas constant. Okay, now the value of this universal gas constant R, it is different for different units. For example, if you are using everywhere the SI units, if you are using for pressure, you are using Pascal, and for temperature, you are using Kelvin. So the value of R is given as 8.314 joule per mole per Kelvin. Okay, joule per mole per Kelvin if you are using the SI system. So in the SI system, the value of this constant R is 8.314. If you are using other units, for example, if you are using instead of the number of moles, suppose if you use kilogram, okay, so the value of the R is different. Generally, we try to use the SI system of units. So you can see there are different values of R depending on the units that we use. If you use bar for the atmosphere, you will have a different value. If you use torricelli's for pressure, you will have a different value of R. So depending on the units, we have different value, but this is the mostly used on the SI system of units. Temperature is measured in Kelvin. So T is for temperature. Okay. So this is the temperature. Now the gases, this equation as it gives a relationship between pressure, volume and temperature, the three thermodynamic variables. We call them as the thermodynamic variables. So this gives a relationship between all the three. Now this value PV equals to nRT, it's called ideal gas equation because we have assumed we have made certain assumptions. Okay, and those gases which follow those assumptions, the gases which follow those assumptions, they are called as the ideal gases. So ideal gas equation, it will be followed by ideal gases only. And in reality, there are no ideal gases because we had made certain assumptions which are not acceptable. For example, we had assumed that the volume of the molecules is very small. It's negligible as compared to the volume of the container. But if the number of molecules is too large, if you have the number of molecules too large and the volume is very small, so in that case, as compared to the volume of the gas, the volume of the molecules becomes, it is not like negligible. Then it is countable. You have to account for it. So for at low volume, if you are studying at low volume, so at low volume, the assumption is incorrect. Similarly, we have assumed that there are no forces of attraction or repulsion between the molecules. That too also is incorrect. Okay. So the ideal gas behavior, this is ideally, if you are accepting everything that is there. So in that ideal situation, the gases will follow this law PV equal to nRT. Okay. So most of the calculations we take this ideal gas equation only. There was some correction which had been put in this ideal gas equation. We will see what are the corrections. So the real gas equation. If you study the real gas equation has a little bit amendment in this equation. The real gas equation is given as P plus A by V squared, and here instead of V you have V minus B equals nRT. So this is the correction that is made. Why the correction? See, B is a constant which will have the dimension same as volume, so that we can assume that B to be the volume of the molecule. So these are the corrections which are applied for the real gases. Okay, we have to do only up to the ideal gases. Another thing we have to do, the relationship between temperature, kinetic energy, and pressure. Okay. So how do the gases exert pressure? So this we have to see. How do gases exert pressure? So how do gases exert pressure? So the gases, they exert pressure by colliding with the walls of the container. Let us see how they collide with the walls of the container. Okay. Gases exert pressure. So, okay, you see. Now consider here a container. Let's have a container with certain gas molecules in it. So we had made an assumption that the molecules of gas, they are in random motion. So the molecules of the gas, they are colliding, they are in continuous motion, and in this way, they are continuously colliding with each other. So there are a number of gas molecules, they are continuously moving. So if we consider out of the molecules, some of the molecules, they are moving towards the x-axis, some of them may be moving towards the y-axis, some may be towards the z-axis. So here, so here, suppose this molecule is moving with the velocity v. This molecule moves with some velocity Vx. We take its velocity to be Vx along the x direction. So this molecule moves with the velocity Vx along the x direction. And now after colliding with the surface, it rebounds. So when it rebounds, when it flashes back, so it has a velocity of minus Vx. If the molecule has the mass m, so we can observe here that there is a change of momentum. Initially, when the object is moving towards the x-axis, it has its initial momentum. The initial momentum is given by mvx. The final momentum of the gas molecule is given by minus of mvx. As here, we observe that the velocity of the particle is now towards the negative x direction. So the final momentum is minus mvx. So we can find to be a change of momentum. Here we have a change of momentum, and that change of momentum would be minus of mvx and divided by time. So we observe here that there is a change of momentum which is equal to minus 2 mvx by t. So you have, sorry, read not t here. We have just found out the change of moment. If you divide it by time, you will get your force. We know that change of momentum per unit time is the force. So this is just a change of momentum. As we can observe that there is a change of momentum. So there is a force that is exerted by the molecules on the walls of the container. Okay. Because as per the definition we know, force is equal to rate of change of momentum. Force is rate of change of momentum. So here we observe that there is some change of momentum. A change of momentum has occurred from minus mv. The change of momentum is minus 2 mvx. So there must be a force, and that force is equal to rate of change of momentum. That is change of momentum by time. So the force exerted by the molecules will be equal to minus 2 mvx over t. So this is just a calculation by which we have shown that yes, the gas molecules, they exert a force on the walls of the container. Now the velocity of the molecules is dependent on the temperature. So greater the temperature, greater will be the kinetic energies and greater will be the pressure. So do you think that are we moving towards the relationship between pressure and temperature at constant volume? Here the volume is constant, and if you are increasing the temperature, the velocities will increase. So more number of collisions will increase, and hence there will be greater force, and by greater force we will be getting a greater pressure. So pressure is equal to force by area. If you divide both sides by area, you will get your pressure exerted by the gas molecules. Okay. So this complete calculation or complete process, how we are getting the uh, each step by step derivation that you will get in the final classes. Currently, we can assume here that yes, the due to the force, due to the motion of the molecules, there is a pressure that is exerted on the walls of the container. And this pressure is finally given by a formula which is 1 by 3 rho v squared. Okay. It's 1 by 3 rho v squared. Okay. So this formulation 1 by 3 rho v squared, we can get this in the form of ideal gas equation also. Remember, rho is here, rho represents density. See, rho represents density, and 1 by 2 mv squared is the kinetic energy. So we can get here, if we combine all the factors, like let's see here, this is the formula P equal to 1 by 3 of rho v squared. So from this, all the assumption which we calculated here, we found the force. Then if we move on, so we will finally get pressure to be equal to 1 by 3 rho v squared. This we will get. Okay. How we get it, that is, you will see later that how we are obtaining here. But this is what we obtain. So from this expression, you can get the other expressions like PV equal to nRT can be obtained from this expression also. See, P equals to 1 by 3 of rho v squared. So rho is mass by velocity, mass by volume. Here you have v squared. You get here PV equals to 1 by 3 multiply mv squared. So you can say PV equals to 2 by 3 multiply 1 by 2 mv squared, multiply and divide by 2. And this 1 by 2 mv squared is nothing but kinetic energy. Okay. So this kinetic energy is a function of temperature. I can put it as 2 by 3 multiply 3 by 2 kBT. Remember, we had done that the kinetic energy is equal to 3 by 2 kV times T. These all cancel, and you have here kV times T. And this kV times T, now you had asked me, sir, what is Boltzmann constant? So if you compare this equation and the ideal equation, PV equals to nRT, and here you have PV equal to KB multiply T. So obviously the value of KB is equal to N multiply R. Number of moles multiplied by the R, that is your KB. So Shashi, yes. Okay, Shashi, thank you for informing. So you got this, that we have understood that pressure volume for the gases, we study things. From this chapter, what all we should be knowing after completing everything, we should know the three laws, three gas laws. That is the Charles law, Boyle's law, and the Gay-Lussac's law. So we have done Charles law, Boyle's law, and Gay-Lussac's law. Okay. So from these laws, finally we obtained PV equal to nRT. This is what we call as the ideal gas equation. This is the ideal gas equation. We can follow some questions based on them. This is the ideal gas equation. Okay. Then we have got this pressure is given by 1 by 3 rho V squared. This is another formula for pressure. Then we also got one more thing from here, that kinetic energy, average kinetic energy is equal to 3 by 2 kT. Okay, so these are some of the important points of this chapter. What after all discussions, we have got these three main points from this chapter: the Charles law, Boyle's law, Gay-Lussac's law, ideal gas equation, and P equal to 1 by 3 rho V squared, K equal to 3 by 2 kBT. Now there is one important question which combines this chapter and the dimensions chapter. So basically, that question is from the chapter of dimensions, chapter 1. Okay, and that question is here. It has been asked in JEE, IIT-JEE long back. The question is, you are given the real gas equation as P plus A by V square. This is P plus A by V square multiply V minus B is equal to RT. So this question is from the IIT previous means it was long back this question was asked. You have to find the value of A and B. The value of not value, the dimensions of A and B have been asked. What will be the dimensions of A and B? Okay. So a very simple rule that we follow in the dimensions. Dimensions say a very simple thing that, okay, Shreyasi, you know this. Fine. See, this is actually based on the rule of the dimensions that you can add pressure to pressure, subtract pressure from pressure, okay, which we call as the principle of homogeneity. So by the principle of homogeneity, you will observe that these two pressures, they are same. These two should be the dimensions of pressure only. Yes. Yes, you are correct. B should have the dimensions of volume. That is, B should have the dimensions of M0, L3, and T0. So this should be the dimensions of B. Very correct. Can you tell the dimensions of A? The dimensions of A. Okay, V squared multiply P. Very good. So the dimensions of A should be equal to V squared multiply A. So you have V squared. V squared is L cube whole squared multiplied dimensions of P, and dimensions of P are ML minus 1 T minus 2. So you have L to the power 6 here, M 6 minus 1 T minus 2. These are the dimensions of A. So from this real gas equation, we can find out these values. In the dimensions chapter, in the next part, we'll be starting with the dimensions chapter. That in the dimensions chapter, how can we obtain or how can we have in the dimensions chapter? how can, if we know the dependence of variables, if we know how the physical quantity depends on certain physical quantity, so we can do some questions. So we can find out over there how we can find out the formula of the physical quantity. Any formula can be found out. Let's see this questions on gas equation. Let's find out. Yes. And for this, so seriously, you can check group. In the group, I have added some questions over there. Let's see and try to solve them. Yeah, Jaswant. Welcome, Jaswant. You joined late.
No, sir. I joined 10 minutes after.
Okay, okay. So see, you have a PDF in the group. Just open it and look for the question. Okay. So in the beginning of this, you can see we have been given P1, V1. That is called as the equation of state. See here, in the beginning, you have been given something which is P1 V1 by T1 is equal to P2 T2. This is called as equation of state. Why we call this as the equation of state? See, we have PV equals to nRT. So if you get here PV by T, PV by T is equal to nR. Okay. So this, if you have the number of moles of the gas to be the same, so this must be a constant. PV by T should be a constant, and hence it should always remain a constant. So this is the initial PV by T. This is final PV by T. So this should be a constant. By this expression, we should get PV by T as a constant, and hence this is also called as equation of state. Okay. Let's see the first question. If I initially have a gas If I initially have a gas at pressure of 12 atmosphere, a volume of 23 liters, and a temperature of 200 Kelvin, then I raise the pressure to 14 atmosphere and increase the temperature to 300 Kelvin. What is the new volume of the gas? So can you find it out? Try to find it out. You just have to use the equation of state. Use the equation of state. Okay, here is the equation of state you have. Yeah, Shashi, they have given pressure in atmosphere, and you think that if you want to convert it to Pascal, so there is no need to convert it to Pascal, as all these are simple ratios. See, you have P1 here, P2 here, so you can get P1 by P2. They are the ratios, so hence no need to convert here. No need to convert to any units. You just put the values. Initial pressure is 12 multiply by initial volume 23 over temperature T1 200 Kelvin equals P2 14 multiply V2 we want to find out over temperature, that's 300. Just simply perform the calculations. Here you have 36 multiplied 23 over 14 is equal to V2. So got the answer for this? Say during the class you can use your calculator. You get something 59.1 liter. So this volume is now 59.1 liter of the gas is V2. So initially if you had the temperature, if you had the temperature 200 Kelvin, increase the temperature to 300 Kelvin, and you have also changed the pressure, still you have a change in volume, that is 59.1 is the new volume. Now the second one, a gas takes up a volume of 17 liters, has a pressure of 2.3 atmosphere and a temperature of 299 Kelvin. If I raise the temperature to 350 Kelvin and lower the pressure to 1.5 atmosphere, what is the new volume of the gas? So I think now you can find out the second one also. Yeah, Yashwant and Shesi, try to find out the second question. It's the same thing in the similar formula. Okay. So have you got the answer for this? You can use your calculator. Okay, try. Just one, try to get it. So all these questions you can practice. All these questions, they are based on just the equation of state. Okay. So the remaining questions, they are your homework. Yeah, 30.51. Okay, Stacy. So you can do the remaining questions. They are your homework from this chapter. Okay. Okay. Bye, all of you. Any doubts from this chapter? I hope we have done this chapter well. And then we can go through in the coming classes, we can go through a revision of all the chapters. Okay. Whatever chapters we have done, we can go through them once more.
Okay, sir.
Okay, and solve them, solve questions now. Now we have done them, we need to solve some of the questions related to whatever we have studied. Okay. Okay, bye all of you.